Okay, so the last topic we saw during the last lesson was the one regarding the evaluation of the energy, or the modification of the energy of the electronic levels due to the presence of the exchange contribution. And the last thing I discussed with you was the, let's say, average, the value of the average energy value for electron, and this was equal to the E divided by 5 times EF, and this was just the average value of the kinetic energy that we saw also in the case of the Sommerfeld model. Then we had minus a negative contribution, 3 divided by 4 E squared KF divided by was that pi square is 0? Is that what? Because I've not here the note that I used during the last Tuesday. Okay. And what we saw was that this term is proportional to kf squared, and this term is proportional to kf. And if we introduce the parameter R0, where R0 is used to, let's say, define a volume, the size of a volume that has a spherical shape that is occupied just by one electron, then we were able to rewrite these two terms as a function of R0, where as R0 is related to the electronic density by this equation. So the number of electrons that you have per unit volume is equal to 1 divided by the volume of this spherical structure where just one electron is found. And the final result was that the average energy per electron expressed in terms of R0 was equal to 13.5 EV divided by R0, sorry, squared. And please note that here we have a power of 2, while in the last lesson I just wrote R0 expressed in Armstrong minus 6.6 EV divided by R0 expressed in Armstrong. And this R0 expressed in Armstrong means if you have 3 angstroms, for instance, you just write here 3 or 3 here and 9 here without unit of measurement, because the unit of measurement is being already included in the calculation. So you just have to consider this energy here in EV and then just divide by the value corresponding to R0. What we saw was that the dependence of the energy, this average energy value per electron divided by R0, was the combination between the 1 divided by R0 squared, that is due to the kinetic term, and the one minus divided by R0, that is due to the potential term. So the final result is that we have here something that goes to infinity when R0 goes to 0, but in this case, the dependence, the leading dependence is the kinetic one, while after some R0 value, then we have a negative value here as predicted, as requested by the potential term, and then at the end, the dependence, the energy goes to 0 as R0, as the value of R0 increases. So the idea is that even if one expects that when R0, so if R0 goes to 0, this means that the electronic density goes to infinity. So you have a very, very dense system. But in this case, the leading term is not the interaction term. So one expects that if you have many, many electrons per unit volume, then the interaction between those electrons should be the leading term. But as we see here, the leading term in this condition is the kinetic term. So this is due to the fact that you try to compress in a very small volume each of all the electrons, and somehow you may interpret this as a sort of trial to localize, to force the localization of the electrons, so that increases the value of the kinetic energy. So in this case, the leading term is not the potential one. The potential term appears, so the energy switches to a negative value only for, let's say, average densities, not for very small densities. So this is, let's say, as those terms there just give us an idea of what is the average energy value. This is on average the result of the combination of the kinetic and of the exchange potential term as we change the electronic density. And some other interesting things appear if we do not focus just on the, let's say, on the average energy value for electron after having performed the integral, but if we focus on the energy versus wave vector dependence that we obtained at the end of the calculation that we performed last time, and this was equal to the, let's say, the typical potential term that we have for free electrons minus the contribution that was due to the exchange energy, and in this case x is equal to k divided by kf, and the expression of fx is 1 divided by 2 plus 1 minus x squared divided by 4x, and then we have the logarithm of 1 plus x divided by 1 minus x. And so this is the contribution of the exchange energy. So this second part here is just the contribution of the exchange term that appeared due to the introduction of the Slater determinant, that is, when we took in account the fact that the full electron wave function has to be antisymmetric with respect to the exchange of two particles. And if you notice here, we have 1 minus x at the denominator in the logarithm. So this is an indication of the fact that when x is close to 1, then the behavior of this function may not be, let's say, may have some problems. And just to make a, let's say, brief sketch of what may be the dependence of the final energy value on the k value, I just make a plot of so if I plot the energy so if I plot this function, so if here we have the energy, here the wave vector, then the, let's say, the free electron contribution is a parabola. So this is just the free electron contribution. If we now focus on the exchange one, Then the exchange one is negative when k is equal to 0. So it starts here. Then if we if here we, let's say, we set this equal to kf, then what happens is this. So here we have something like, oops, we have something like this. Yeah, so we have a strong decrease of the energy for small values of the wave vector. Then this decrease is diminished and then goes to 0 as the value of as the value of k increases. If we just plot the let's say fx dependence, so if this is kf and we plot here the let's say absolute value of the exchange term, where the exchange term is this one here. So I just here plot the positive value, then we have something like this. So something that decreases, we have a change of curvature here, and then the term goes to 0. So we have that the strongest deviation, I'm sorry, I just make one comment. In principle, the value here should be 1/2 of the value here. So this picture, I try to make the, try to do the correct picture. Yeah, so something like this should be expected. So the value of 0 is twice the value that we have at kf. And yeah, so the strongest deviation from the free electron value is found for low values of the wave vector k, and then the difference with respect to the free electron situation goes to 0 as k increases. But if we now look at the fx dependence, this is again if we look at what happens to fx when x is close to 1, then this is equal to 1/2. Then this 1 minus x squared can be written as 1 minus x times 1 plus x. So here we have 1 minus x times 2, because 1 plus x is nearly 2 when x is close to 1. Then we have here 4 times x, but if x is close to 1, that is 4. And then we have the logarithm of 1 plus x is close to 2, and then we have 1 minus x. So we have 1 minus x here at the numerator, and within the logarithm we have 1 minus x at the denominator. So in principle here we should expect a divergency due to the fact that what we have within the logarithm goes to infinity as x goes to 1. But as this logarithm is multiplied by 1 minus x, then this term, the limit of this term when x goes to 1 is equal to 0. So here we have just 1/2. So this means that the actual value of the energy, as we see from this picture, has no, let's say, the behavior is continuous, even if we have here this 1 minus x at the denominator. The actual problem is found when we consider not the value of the function when x is close to 1, but the derivative of that function when x is close to 1, because the derivative of the energy versus wave vector dependence is the velocity. So let's say one of the things we may have to do when using that function is, for instance, to evaluate the velocity of the electrons that are close to EF, because x equal to 1 means, so x is defined as k divided by kf. So when x is equal to 1, we actually are at the Fermi surface. So that is an important region to investigate when we consider the properties of the systems. So in case we evaluate the derivative of f with respect to x, at this point, if we use this approximate expression, then we have this just 1/2 here. So here we have a product. So we make the derivative of that. We have just 1/2 times the derivative of a first term, that is -1. And then we have the logarithm of 2 divided by 1 minus x. Then we have the first term times the derivative of the logarithm. And if we suppose, just to, let's say, assume that 1 minus x is positive, if we suppose that the limit when we consider x going to 1 is from 1 minus, so we are approaching 1 from values of x that are smaller than 1, then 1 minus x is positive. So I may just remove the absolute value and leave there 2 divided by 1 minus x. At that point, I have 1 minus x divided by 2 times the derivative of that, that is this one here. So this is something that doesn't depend on x when we, because we have 1 minus x squared here and 1 minus x squared here. So at the end, this is just a constant term. But we have this logarithm of 2 divided by 1 minus x. So when x goes to 1, here we have a divergency. And this is a great problem, as the divergency is exactly found for x close to 1. So when k is equal to the Fermi wave vector. So this is a strong problem, as if we use this approximation to evaluate the exchange energy, then we are not able to evaluate the velocity of the electrons at the Fermi surface. So we do not know what is the velocity of the electrons that give a huge contribution to the properties of the system. So the question here is, where's the problem? So why does this function here displays such a divergency? And at this point, due to that, we are not able to, let's say, draw a physical assumption or physical comments concerning the problem, the system we are investigating. If you remember the origin of fx, fx or f of k divided by kf is related to the integral that we performed during the last lesson. And that integral was linked to the summation of 1 divided by m minus k squared. This was the Fourier this 1 divided by m minus k squared was obtained as the Fourier transform of the Coulomb potential, because in the integral at the beginning we had 1 divided by r times a phase, and within the phase we had m minus k. So we were evaluating something that was proportional to the Fourier transform of the Coulombian potential evaluated at the value of the wave vector that is equal to m minus k. So the starting point of the calculation was, let's say, an integral involving the Fourier transform of the Coulomb potential. And if you notice, one of the details of this potential is the fact that, as now I change page, as the wave vector value where you want to evaluate the, if we use the, let's say, Coulombian potential, and we make the Fourier transform of that, then we have something that is proportional to 1 divided by q squared. Here we have that when q goes to 0, then 1 divided by q squared goes to infinity. So what is the physical meaning of that? The physical meaning of that is the following. When q goes to 0, that means that you are making the Fourier transform using a wave vector that is very, very small. If the wave vector is small, this means that the wavelength corresponding to that wave vector is going to infinity. So the idea is when the value of the wave vector goes to 0, you are making the Fourier transform of the potential, and you are going to investigate what is the Fourier transform corresponding to a wavelength that is very, very large. So a very large wavelength means that you are sampling the value of the potential over all space. So when q is equal to 0, then the Fourier transform is equal to let's say when q is equal to 0, this term disappears because that is equal to 1. So at this point, you are making an integral over the full volume, the full space, with no phase. So you are making a sort of average of the Coulombian potential over the whole space. Due to the fact that the 1 divided by r dependence, what happens to the 1 divided by r dependence? If you, let's say, even if the distance, if you suppose that your particle, your electron, for instance, is at the origin, even if you move far away from the origin, so even if you increase r, then the volume of other particles that are found in that area, the number of particles that are found in that area increases as you increase r. So the value of the potential decreases, but the number of particles that interact with your electron increase due to the fact that you increase this volume. So due to that, you may say that the Coulombian potential has a long range of interaction. So even if you move far away from the, let's say, from the origin, from where you put the charge that produces this potential, all the other charges that interact with that charge, even if they are far away from the origin, give a contribution to the interaction. And this is different from, for instance, a potential that has, let's say, if I had the potential having this shape, for instance, so if I had the potential with an exponential dependence on the position, then if I have this shape, I know that after a value of r that is of the order of 3d0, then the interaction can be neglected. So this is a short range potential. So if I had something like this, then this problem would not be there, because we have a strong cutoff that is observed for a distance of the order of 3d0, and after that the contribution of the potential is nearly can be neglected. But this is not the potential, the Coulombian term, because the Coulombian term has not any potential cutoff, sorry, any exponential cutoff. It has just a 1 divided by r dependence. So the main problem here is due to the fact that the Coulombian potential has a very long range of interaction. So that is the source of the problem that we find in correspondence of K equal to Kf into the exchange contribution. Because again, the exchange contribution was obtained directly from an integral where we had the Fourier transform of the Coulombian potential. So at this point, the question is it possible to, let's say, change the approximation that we use for the expression of the Coulomb of the interaction potential? Because up to now, I've always used, for what concerns the interaction potential, the expression 1 divided by 4 pi E0 times 1 divided by r, and then we have the charge of the electron. So up to now, I always use this expression for what concerns the potential that is produced by one electron. In this case, we have, sorry, here we have E0. So this means that we are considering the fact that the electron and all the other electrons are included in vacuum. But here, we are not actually in vacuum, and in particular, we have just started to investigate what happens when we consider the electron-electron interaction. For the moment, we have investigated what happens when we switch on the electron-electron interaction, and we want to investigate how the energy value of each electron changes. But there is another mechanism that sets in when we switch on the electron-electron interaction. If you suppose, just to make an example, if you suppose that here you have, that in this volume, you have electrons. So let's suppose we have a metal. So here we have ions, electrons, and let's suppose that the density of electrons is uniform initially. Then if we introduce in this system an external charge, so let's suppose to have here, just to make an example, a positive charge that I call external, as that charge is not a part of the solid, but is just something from the outside that I put into the solid. Then if I put this charge here, then what happens? This is a positive charge. So the positive charge attracts the electrons. So here, what I'm supposed to observe is an increase of the electronic density, because the positive charge attracts the electrons that are available here in the system. Due to the fact that the presence of the positive charge increases the electronic density close to the charge itself, this means that if you look from here at what happens, you have that the positive charge that produces a positive potential is surrounded by negative charges that have a density that is larger than the density of the negative particles in the solid. So the presence of those additional particles here produces a sort of screening of the positive charge. So if you look at what happens from, let's say, not directly from there, but if you are slightly away from that point, you do not see the full potential of the external charge, but you see the potential of that charge decreased by the fact that you have an additional contribution coming from the internal charges that try to, let's say, screen the contribution of the additional charge that you have injected in the system. So what is the conclusion? The conclusion is that apart from the exchange contribution that is due to the correlation between the electrons, we may suppose to have an additional contribution due to the fact that for any charge that you have in the system, the electrons may redistribute into the system. So depending on the sign of the charge that you inject. So if you have a negative charge, then you produce the opposite effect. So you have a diminishing of the electronic density close to the charge. So you have a sort of increase of the positive density charge close to the external charge in case that is negative. So we have exactly the same phenomenon, but just reverse for what concerns the sign. So the idea is the electrons, as they are fast particles, are able to rearrange their configuration depending on what happens to the system from the point of view of the charges that you have in the system. So the idea is that what happens here for an external charge will also happen for the electrons. So if you are an electron and you move into the system, the other electrons feel your charge, so they redistribute, they change their configuration to let's say, due to the fact that you electron, let's say a negative charge, are moving in between negative charges. So all of the electrons belonging to the system interfere with all the other electrons and produce a reconfiguration of those electrons. What is the, let's say, name that we attribute to this sort of reconfiguration? The name of that is the same that you, let's say, if you remember what happens when you consider a dielectric system, when you consider the Coulomb potential produced by a charge that is equal to Q, when you put the charge not in vacuum, but in a dielectric medium, then the value of that potential is not 1 divided by 4 pi E0, but is 1 divided by 4 pi times the permittivity, the permittivity of the system you consider. So, and in general, the permittivity is equal to E0 times the relative permittivity. So in general, what you expect to have here is that the potential term of that charge in the dielectric medium is smaller than the value of the potential when the same charge is placed in vacuum. So the idea is we expect that this reconfiguration, so the fact that the charges of the system rearrange themselves due to the presence of an additional charge, may produce an effect over the permittivity of the system. So what we expect is that the effect of the electron-electron interaction will also affect the permittivity of the system. So the dielectric constant of the system is expected to change if we let the electrons to be free to move depending on, again, external charges or also to internal charges, because during the motion of one electron, he has to take into consideration the motion of all the other electrons. So at that point, the motion will not be exactly a straight line, because that has to take into the consideration also the motion of all the other particles. And the idea that can be used to handle this mechanism can be extracted from this expression. So if you notice here, the potential, if you don't mind, instead of writing V, I will use another letter because that is the letter that is used in the text. I will call the potential equal to phi. So phi is the potential. So phi is the potential in the dielectric medium and is equal to this expression. You may write this as 1 divided by 4 pi E0 times 1 divided by the relative permittivity times the charge divided by R. If you notice this, here is, let's say, if this is an external charge that you put into the system, then this is exactly the potential of the external charge if that charge was in vacuum. So what we have here is that the potential in the dielectric medium is equal to the potential of the external charge if the external charge was in vacuum, divided by the relative dielectric constant of the medium. So we have that the external potential is equal to the actual potential in the medium times the relative dielectric constant. So I will start from this equation to try to estimate the relative permittivity of the system in case we consider the contribution of the electrons. So the starting point is that the potential is equal to the potential in vacuum, or the potential of the external charge by itself without any contribution due to the polarization, times the relative permittivity. This expression is fine if we suppose to have an isotropic uniform dielectric medium. So if the contribution of the dielectric constant, if the permittivity is just a coefficient, at that point this expression is fine. But in principle, we may, if we want to use a more general expression, the more general expression is the following. So the actual potential in the system is equal to the convolution between the external potential in position r prime and the relative dielectric constant that depends both on the position r when we want to evaluate the potential, and the position r prime where the external potential is evaluated. So in general, just to use a more general expression, one expects to put here not just a number, but something that depends on the position where you want to evaluate the potential, and also the position where you are actually evaluating the external potential. At this point, to solve this equation, let's say, to handle this equation in an easier way, one makes these approximations. One approximation is to be in an isotropic system, and this is a strong hypothesis because on a short scale, the lattice is not isotropic, because on a short scale, the ions are, let's say, the ions occupy fixed positions. So in general, you may not say that the lattice is isotropic. The lattice is isotropic only on a very long scale. When you average, let's say, you do not focus on the specific position of all the ions, but you just have a look on average on the distribution of the charge on a long scale. So assume that the solid is isotropic means assuming something like you had, let's say, free electrons, because you assume that the charge of the system, the positive charge of the system is uniformly distributed. So this hypothesis is just to say a sort of, let's use the free electron approximation, because otherwise you have to use this complex expression for the relative permittivity. And a consequence of that is the following. If the space is isotropic, then if you're supposed to be in position r prime, then the value of E of r that depends on both r prime and r should not depend on the absolute value of r and r prime. So if the distance between those two values, r and r prime, is, for instance, 1 meter, and then you make a translation, but the distance between r and r prime is always the same, then you should expect that E of r has to have exactly the same value. So E of r should be invariant under translations. This expression of E of r is not invariant under translations. So to have an expression of E of r that is invariant under translations, what you do is to write that E of r does not depend on the absolute values of r and r prime, but depends on the difference. So if E of r depends on the difference, then this is invariant under translations. So in this way, we apply the isotropic approximation and we rewrite the expression of E of r. Even with this simplification, this is an equation that is hard to solve. So since this here appears to be a convolution between the external potential and the permittivity, there is a theorem that tells us that if we, instead of using the, let's say, expression of these quantities in the direct space, if we work not in the direct space but in the Fourier space, the convolution between two quantities in the Fourier space becomes the product of those quantities. So the idea is to switch from the representation of the potential using the direct space representation to the representation of the potential using the Fourier transform of the potential. So if we use the Fourier, so if we use the Fourier transform of the potential, then this equation becomes value of the Fourier transform of the potential corresponding to wave vector q is equal to value of the Fourier transform of the external potential corresponding to q times relative permittivity corresponding to the same wave vector. So in this configuration, the equation is way easier with respect to the initial one. So we use this as a starting point of the calculation. At this point, we may use other equations relating, let's say, the external potential is due to the fact that we have an external charge. This external charge may not be always, let's say, a point charge. So we may have an external charge density distribution that produces the external potential. So we have a charge density, the external charge density, related to this potential. Due to the same motivation, we have that the actual potential is related to the actual charge density into the system. And the actual charge density into the system is equal to the external charge density plus the induced charge density. So the external is just the charge that you put into the system. The induced is the charge that is due to the electrons into the system that rearrange their positions due to the fact that we have this mechanism of reorganization, redistribution of the position of the electrons within the system. And just to make a comment, if you remember the, is that correct? Yeah. No, sorry. I wrote one thing and I did exactly the opposite. Sorry for that. Here, I'm sorry, I didn't notice that. here I wrote that the actual potential is the external times the dielectric constant. So I'm sorry, I have to. Yeah, so the external one is equal to the actual potential times the relative permittivity. And if you remember the Maxwell equations, when you at the bachelor degree try to rewrite the Maxwell equation considering a dielectric medium, this is the equivalent of that, because E is the actual electric field that depends on on all the charges, external charges, induced charges. So E is due to all the contribution of the rearrangement of the charges into the system. D is the displacement field, and the displacement field depends only on the external charges. And since there is a connection between the field and the potential, because the field is the minus the gradient of the potential, so a similar relation that takes place between the fields can be observed considering the potentials. So at this point, we have, again, the connection between the potential and the charges. So we have the external potential related to the external charge, and the full potential into the system related to the full charge density into the system, including both the external term and the induced contribution. There is another, just we need one more equation to solve the problem, that is the following. We know that the gradient of the electric field is related to the gradient of the potential. So the field is related to the potential, and the divergence of the field is related to the density charge. So we have an equation that relates the potential and the density charge, and that equation is the Poisson equation. That is that in the direct space, we have that minus nabla square of the potential is equal to the value of the charge, the charge density divided by E0. So this is in the direct space. If we switch to the Fourier representation, this is a second derivative applied to the coordinates. Since we have this derivative applied to the coordinates, if you apply that to the Fourier transform of the potential, then a q squared term must appear. And then we have the disappearance of the minus sign due to the phase that we have into the expression of the Fourier transform. So we have q squared times the potential evaluated at q is equal to the charge density evaluated at q divided by E0. So from this equation, we may say that the induced is equal to the total, to the full charge density minus the external one. And yeah, if you remember, when you describe the dielectric medium, one of the equations that are used is the following. So you write down the depolarization of the system, that is the P is related to the induced charge density that you have into the system due to the fact that the charges in the medium are able to redistribute if you apply an external electric field. This is equal to E0 chi times the electric field in a linear approximation. So you assume a proportionality between the polarization we observe and the electric field. Due to the fact that the fields and the charge density are related with each other, because the E is related, the divergency of E is related to the actual charge density, and the divergency of P is related to the density of polarization. That is what I called here induced density charge. You assume that the induced density charge is proportional, and the proportionality using the same symbol is written as chi, to the full potential that you have into the system. And just to be more general, just to use a more general expression, I may just write T of Q, just to be more general. So using exactly the same approach here, so the polarization of the system is proportional to the actual value of the electric field into the system, I use this equation. So the induced density charge is proportional to the, I expect that to be proportional to the actual potential that I have into the system. So at this point, if I rewrite the induced, let's say, the induced charge density is equal to the actual value, the full value of the charge density, but the full value of the charge density is related to phi, because we may use this equation. So in place of writing full value of the charge density, I write Q squared potential times C0. So this is Q squared times potential times E0 minus the same expression, so Q squared external potential times C0, and this is equal to chi and the value of the actual potential. At this point, if I consider this equation, includes both only phi external and the full value of the potential. That is the same situation that we have here. So if I use the last equation to express the external potential as a function of the full potential, then I may have a closed equation to relate the relative permittivity to chi. Then the problem will be to find chi. But first step is to relate relative permittivity to chi. So in this case, if we divide everything by Q squared, we divide then we have that the phi external, and I also divide everything by E0. We have that phi external is equal to the full potential with times 1 minus chi divided by Q squared is 0. And this, due to the equation that I wrote before, is equal to actual potential times relative permittivity. So now we have a connection between the let's say what was the electric susceptibility of the system and the relative permittivity. The thing we now miss is the value of chi, and yeah, if for you, do you mind if now it's 10 past 10? The evaluation of chi is quite simple. So if you don't mind, I just evaluate that and then I make the break. Yeah. So the problem now, again, is to find the susceptibility. I just rewrite the expression of E of R. It is 1 minus chi of q squared E0. Chi of q chi of q was the proportionality constant between the induced charge density and the actual potential that we have in the system. How can we evaluate the induced charge density in the system? The solution to the problem is the following. Due to the fact that we consider this approximation, so we suppose that the system is isotropic, so the charge density of the ions is uniform. This is equivalent to say we are like of using free electrons. If we use free electrons, then the Schrödinger equation should be this one here. But in this case, we have to handle the fact that the electrons in the system are not just under the effect of, let's say, the electrons in the system, in this case, are under the effect of the external potential. This external potential, if we want to introduce this external potential in the Schrödinger equation, then we should write minus E times this external potential times the electronic wave function. So at this point, how is it possible to solve this equation? It is possible to solve that equation if we assume that phi of R displays a slow variation. So this means that phi of R, let's say if we plot the value of phi as a function of the position, phi of R may have a variation. So it's not said that it has to be uniform. That may change from point to point. But if we assume that the scale of variation, so if lambda is larger and larger with respect to the, for instance, to the mean free path So if that is larger and larger with respect to the mean free path of the electrons, then what happens? Then over one mean free path, the electron sees that the potential is nearly uniform, because from one scattering event to the next, the electron does not feel a strong variation of the potential. So due to that, if this is correct, then I may write that the energy of the system, that the energy of one electron is equal to the energy that I have in the free electron approximation minus the energy that corresponds to the presence of that potential. So at this point, it's just like as if you solved a Schrödinger equation using as phi a constant value. So if that is a constant value, then you may just put that value into the energy. So the application of an external constant potential induces just a shift of the energy of the electron. So in this case, if we make this assumption, then it's easy to rewrite the value of the energy, and at this point, we may evaluate the electronic density by making the usual integral. So we can evaluate this integral to evaluate the charge density, and just to so if you include the effect of the potential into the chemical potential, and if we assume that the external potential is not strong, so can be considered to be just a perturbation. So if E times phi is small with respect to the value of the chemical potential, then we may say that the induced charge density is equal to minus C times the density of the system corresponding to phi minus the density of the system when phi is equal to 0. So in general, this is the density when we apply the external potential. When phi is equal to 0, we have the equilibrium density. And if phi can be considered a perturbation, so if E times phi is smaller and smaller with respect to the value, the actual value of the chemical potential, then this term here can be considered to be minus E times, we may write this difference as derivative of n with respect to the parameter we are changing here is the chemical potential. So this is a derivative of the density with respect to the chemical potential times the perturbation. And the perturbation in this case is E times phi. So what we have is that the induced charge density is minus E squared times derivative of n with respect to the chemical potential times the potential. So we have an equation that relates the induced charge density and the potential. And this coefficient here, so minus E squared times the derivative of n with respect to the chemical potential, does not depend on the external potential. So this is just a coefficient that depends on the, let's say, on this integral on the Fermi distribution function, but that doesn't depend on the chemical potential. Sorry, does not depend on the actual value of the external potential. So we may introduce this expression into this equation, so to have that E of R is equal, and that doesn't also depend on the position, because if we consider n when phi is equal to 0, then we have no position dependence in the integral, so that doesn't contribute to the Fourier transform. And then we have 1 plus 1 divided by q squared is 0 times e squared derivative of n with respect to the chemical potential. Since e squared is a constant, E0 is a constant, the derivative of n with respect to the chemical potential is again a constant. To simplify this expression, one generally writes 1 plus Q0, not Q0, just to distinguish that from Q, I call that K0 squared divided by Q squared. So K0 squared is just a coefficient, a number, divided by Q squared. So at this point, we have a new expression for the relative permittivity of the system, and that expression was obtained starting from this general expression that, let's say, this is just due to the use of the general equations that can be used in any case. So this is not specific for the electrons. The connection with the electrons is just due to the use of the actual expression for the electronic density that if we have 4 electrons. And this approach, based on the use of a phi of r that displays a slow variation in space and uses this expression for the electronic density, is called the Thomas-Fermi approach. So this approach is able to relate chi, that is again a general term, to the specific situation where we use, we suppose to consider the electrons as particles that rearrange themselves due to the presence of an external potential. So in case that potential is not so rapidly, displays no fast variation, then we have this expression for the relative permittivity. Okay, so do you have questions or comments? Also, for those who are connected, are there any questions or comments? Okay, so I stop the registration, then we can make the break.